Now let's start talking about Chapter 10, Forecasting. Forecasting is about predicting the future, and obviously that is a very difficult job. At the same time, there are many different and sometimes conflicting needs for forecasting within any business. No matter how good or bad a forecast is, you still have to make one because many functions require a number to work with. Even if that number turns out to be inaccurate compared to the reality, it is still necessary to plan and decision making. On this slide, you do not need to read this whole table in detail. It simply shows how different business functions rely on forecasting in different ways. For example, think about new product introduction. In this case, we usually need a medium range forecast and meaning the time horizon of perhaps maybe 18 months to 2 years. Okay. In terms of accuracy, no one really expects a very precise prediction that far into the future. So there is understanding that uncertainty will be relatively high. Okay. So that's accuracy expectation. The number of forecasts is usually limited, often a one-time estimate for that specific product. And because this is a strategic decision, it typically involves, input from top management. Now consider, let's say, another example such as labor planning. This also usually involves a medium range forecast, perhaps 3 to 8 months ahead, because hiring, training, and laying off employees take time. The required accuracy is moderate. It does not need to be extremely precise since future conditions will change. And the number of forecasts may be updated occasionally, but not very frequently. In this case, decisions are more operational. So managers at the departmental level play a key role based on their budgets and staffing needs. If you are wondering which activity require more frequent forecasting, look at pricing decisions. Prices often need to be adjusted as the market and competitors change. Similarly, cost estimate may also require frequent update. Okay, so all those input factors such as labor, material, transportation costs, they constantly change. Later, you can visit this table and connect these different forecasting needs with the appropriate forecasting method. At this moment, we haven't introduced them. Okay, you will get those connections more maturely later. So let's leave it for the future. On this page, we are looking at a similar idea as the previous one, but now the focus is specifically on decisions and activities related to operations management. What you can see is that the need for forecasting appears everywhere, from very strategic decisions all the way to short-term operational activities. For example, at the strategic level, we have decisions like process design or capacity planning and facility planning. Okay, so such as determining how large a factory or building should be. This type of decisions require forecasts that extend far into the future. Because the time horizon is long, we have to accept a moderate level of accuracy. Typically, these forecasts are done only once or a few times, since once the decision is made, it is difficult to change. As a result, these decisions involve top management. Okay, so on the other hand, let's look at a really short range activity, such as inventory management. The situation is very different. Here we are concerned with what will happen in the next few weeks. So the time horizon is short. The required accuracy is much higher because these decisions directly affect day-to-day operations. Forecasts in this area need to be updated frequently, sometimes weekly or even daily, as inventory levels and replenishment needs change. These activities are usually handled at a lower management level and can often be supported by functions like marketing. You can take some time to read through this page in more detail and think about other examples that may fit into these different categories. When we think about forecasting, we often think about number crunching, right? Number crunching. And that is true in many cases. However, there are situations where we need to use qualitative forecasting methods instead. This usually happens when we do not have historical data or when something fundamental has changed. For example, consider the launch of an entirely new product. Okay, not just as a minor update or a variation of an existing model or something. In that case, there is no past data to rely on. A classic example would be something like the introduction of iPhone back in 2007. Similarly, even if data exists, it may no longer be useful if conditions have changed significantly, such as when a new and powerful competitor enters your market. In these situations, historical data becomes less relevant, and we need to rely on qualitative approaches. Qualitative forecasting often involves managerial judgment, where experienced executives come together to discuss and form an estimate. It can also involve marketing research or marketing survey, such as a focus groups or consumers, interview happens, especially for new products. Another approach is use life cycle analogy, uh, where we consider whether the product is in its introduction stage, growth stage, maturity, or declining stage to guide our expectations. This There is also a more structured method called Delphi technique. In typical group discussion, whatever the format, this is a technique applied for many of this format. Okay, so in the typical group discussions, one or a few individuals may dominate the conversation due to various reasons, maybe due to their personality, maybe due to their rank and tenure. So the dominant participants leading the others to follow their opinions. This can result in group thinking, where the outcome reflects influence rather than true consensus. The Delphi technique is designed to avoid this problem. In this approach, experts provide their opinions independently, and their identities are kept anonymous. A mediator collects these responses, summarizes them, and then creates a new round of questions. Participants review the summarized feedback without knowing who said what, and then they revise their opinions as needed. This process is repeated for a few rounds, and the goal of gradually moving towards a consensus. That's a goal. Okay. The final consensus then serves as the qualitative forecast. So even though qualitative forecasting does not rely on numerical data, it can still follow a structural and disciplined process rather than just an informal discussion. Okay. Now let's move on to numerical or quantitative approach of forecasting. The main approach we will introduce is time series analysis. A time series is simply a sequence of data points recorded at constant time intervals. Okay? In time series forecasting, what we are trying to do is use the historical patterns in that data to make predictions about the future. So what do we mean by patterns? First, there is a pattern called level, meaning the data stays at a roughly stable baseline. That is the basic tone of the forecast. Second, there may be trend, meaning the data is generally moving upward or downward over time. Third, there is seasonality, which refers to recurring cycles over a short period. For example, if you look at a restaurant's sales over a course of a week, Friday evening may constantly consistently be the peak period, while Monday or Tuesday evening may consistently be low demand periods. These patterns repeat regularly. When a cycle occurs within 1 year, we call it seasonality. It may be tied to a season, may be tied to a month, a week, or even a day. On the other hand, some cycles last longer than 1 year. These are usually driven by broader economic conditions, such as interest rate, credit market, or other major economic forces. These longer cycles may last 3 years, 7 years, or even longer. Finally, there is random error. This is the unpredictable part that is always present as small day-to-day fluctuations. These are the main elements of what we call demand pattern. Okay, so if you look at this chart, the actual demand on the left, appear as one that combines many different patterns. Okay, but through analysis, we can break it down into the major components. We can find such as actually this is the cycle we can observe. All right. And we can see seasonality, for example, here, here, and here. These are the typical seasonality among these two cycles, right? And such as trend, the overall trend for this curve is slightly moving upwards, and and all this fluffy, the remaining random error that's make this one not so smooth, the fluffy nature. That's the random error. Okay. So this is the idea behind time series forecasting. We try to predict the future by identifying and analyzing these patterns in past data. The most basic time series method is the moving average. Do not be intimidated by the equations in the textbook because they are describing a very simple idea. Let's start with the simple moving average. The concept is to use the average of the most recent actual demand values as the forecast for the next period. For example, when we say MA, meaning for moving average, MA3, it means we take the most recent 3 data points, calculate their average, and use that as a prediction for the next period. It is as straightforward as that. Okay? A natural question is how many data points we should include. Should we use 3 or 5 or even more data points? The answer depends on the balance we want to achieve between smoothness and responsiveness. On one hand, we want the forecast to be smooth because we use it for planning productions, planning purchasing, or other decisions, and we do not want it to be fluctuate wildly. On the other hand, we also want the forecast to respond quickly to real changes in demand. If demand is increasing, we want the forecast to reflect that as soon as possible. Using fewer data points makes the forecast more responsive but less smooth, while using more data points makes it smoother but slower to react. So choosing the number of periods is essentially about finding the right balance between these two goals. A variation of the simple moving average is the weighted moving average. In the simple moving average, each data point has equal weight. For example, in MA3, each of the 3 observations effectively has a weight of 1/3. However, in many cases, we prefer to give more importance to recent data so that the forecast can respond more quickly to changes. In a weighted moving average, we assign different weights to each data point. For instance, we might assign a weight of 0.5 to the most recent observation, 0.3 to the next one, and 0.2 to the oldest data. The key requirements are that all the weights must be between 0 and 1, and they must sum up to 1. If we increase the weight on one observation, we must decrease the weight on others. Typically, we give higher weights to more recent data. Because of its simplicity, the moving average is widely used in basic forecasting situations. You may also recognize it from stock charts, where you often see such as this curve as, the red one is MA5, green is MA10, and MA25, etc. These lines are simply moving averages with different numbers of periods. In the next slides, we will go through a very simple numerical example. On this page, the left-hand side shows a very simple numerical example. You are given the actual demand for period 1, 2, 3, and they are correspondingly 10, 18, and 29. The question is how to forecast period 4. The idea is straightforward. Assuming a moving average of 3, we simply take the average of the three numbers. So the forecast for period 4 is 19. Okay? Now, how do we forecast period 5? For that, we need to wait until we observe the actual demand for period 4. Once that number is given, we take the most recent actual demand or most recent actual observation, and just take the average again. But remember, this time they are period 2, 3, and 4. These three numbers. Okay? And the data from period 1, which is 10, is now too old and should not be included in this MA3 calculation. So the moving average always rolls forward using the most recent data. On the right-hand side, this chart shows the smoothness and responsiveness balance. The black curve is the actual demand, which fluctuates quite a bit. The orange one shows the MA3 forecast. Okay, notice that it starts from period 4 because we need to have at least 3 data points before we can calculate the first forecast. There is also a green dotted line, which is actually MA6. You can notice they start from period 7 since it requires 6 data points to begin with. If you compare the orange versus the dotted green, you can see that the green line is smoother and less volatile. However, it also reacts more slowly to change in demand. The orange line, using fewer data points, responds more quickly, but is less smooth. You can see it's less smooth. Okay? This illustrates the trade-off between smoothness and responsiveness when choosing the number of periods in the moving average. Now let's introduce another time series method called exponential smoothing. In practice, especially in business application, this method is used much more often than the moving average. In fact, it is the foundation of many modern forecasting tools. Okay, let's look at the equation. But do not be intimidated by the notation. Okay, F stands for forecast. So F for period t plus 1 means the forecast for the next period, t plus 1. This equals the forecast from the previous period, which is ft, plus a correction term. Okay, the correction term is alpha multiplied by the difference between the actual demand in period t and the forecast in period t. Okay, here alpha is called a smooth factor. Okay, smoothing factor. It's a number between 0 and 1. Normally, it's something lower, such as 0.2 or 0.3. Okay, so what's this idea? The idea behind this equation is very intuitive. We start with our last forecast and then adjust it based on the arrow we just observed. If the actual demand is higher than our forecast, then the difference is positive, meaning we underestimate. So we adjust the next forecast upwards, right? So if the actual demand is lower than the forecast, then the difference is this one will be a negative number, and meaning we overestimate it and we adjust the next forecast downward. This is why exponential smoothing is considered a self-correcting method. The smoothing factor alpha controls the balance between responsiveness and smoothness. Okay? If alpha is large, the forecast reacts quickly to changes. In the extreme case where alpha equals 1, the next forecast is simply the most recent actual demand, which is very responsive, but also very unstable, right? On the other hand, if alpha is small, such as 0.1 or 0.2, the forecast changes more gradually and is smoother. Let's look at this simple example, okay? Suppose the forecast for September is 15 units, and the actual demand turned out to be 14 units. Actually, let's say 13 units. If alpha is 0.2, then the forecast for October will be the previous forecast of 15 plus 0.2 times the difference between the actual and forecast, okay, which is 13 minus 15, okay? So this results in a forecast of 14.6, reflecting a small downward adjustment. Look at the chart. The black curve is still the actual demand. The orange curve with a higher alpha, such as actually is 0.3, responds more quickly to changes. Well, the green dotted line with a smaller alpha which is 0.1, is smoother and change more slowly. Another advantage of exponential smoothing is that it is very efficient. You only need the most recent forecast and the most recent actual value to keep updating, keep moving on with the forecast. Well, you only need two numbers, okay? And you can start as soon as you have the first pair of data, so they don't need to wait until, period 6 or 7. It's right here, okay? So you can start there. So that's very strong benefit of exponential smoothing. Now, let's talk about forecast accuracy and how we measure it. We need this measurement for several important reasons. First, they help us monitor for outliers, so we can detect unusual or exceptional situations and get alerted when something is off. Second, they help us detect model breakdown. A forecast method may work well for a period of time, but if the underlying conditions change, such as a new competitor enters the market or a regulatory shift, the model may no longer perform well. By tracking accuracy, we can identify when performance deteriorates and reassess whether the model is still appropriate. Third, accuracy measures help us choose parameters. For example, if we are using a moving average, we need to decide whether MA3 or MA5 or MA6 performs better. We can compare their accuracy and select the one with the lower error. To do this, we start by defining the error terms for each period as the actual value minus the forecast. At this stage, we are not generating forecast, but evaluating the performance of existing forecast, and we are already given two columns of data, the actual and the forecast. For each pair, we calculate how far apart they are, okay, for each pair. Then one common measure is MAD, or mean absolute deviation. We take the absolute value of each arrow, sum them up, and divide it by the number of observations. The reason we use absolute value is to prevent positive and negative arrows from canceling each other out, which would underestimate the true level of inaccuracy. Another measure is MAPE, mean absolute percentage error. This is very similar to MAD, but it expresses the error as a percentage. This makes it easier to compare across different contexts, especially when the scale of the data differ a lot. For example, comparing error between a large operation and a small one is more meaningful when expressed in percentage terms. A third measure is MSE, or mean squared error. Here we square each error before averaging. This not only ensures our values are positive, but also gives more weight to larger errors. As a result, MSE highlights situations where there are occasional but significant deviation. Different measures are useful in different situations. For example, in a relatively low risk setting like toy sales, MAD may be sufficient, and it's quite intuitive. But in a high stake environment such as power grid planning, large errors, large forecasting errors, okay, large errors can have serious consequences. As a measure like MSE, this one, MSE, is more appropriate because it emphasizes those extreme deviations. Of course, there are more advanced methods for forecasting beyond the basic ones we have discussed. The simple approaches like moving average and exponential smoothing are limited, especially when the data include trends or seasonality, right? To handle those situations, there are more sophisticated methods such as adaptive smoothing, Box-Jenkins. You only need to be familiar with their name at a certain point, but these methods are designed to be better capture complex patterns in time series data. Another major category of method is causal or regression models. Instead of just looking at patterns in the data, these models try to identify the underlying drivers of change. By understanding the relationship between variables, we can use those factors to make forecasts. The textbook covers these regression models in detail, but we will not go into them here. And for this course, I will not require them. Okay, so ignore those corresponding sections. Finally, with the development of big data analysis, we now have even more advanced approaches. These methods often combine different techniques, including time series and other models, to handle very large data sets with more sophisticated analysis and visualization. However, those approaches are beyond the scope of our current discussion. Okay. The last page focuses on how forecasting is applied in practice. Forecasting is not just a passive estimate of future demand. In reality, demand is influenced by many factors, including actions taken within the supply chain itself. Because of that, forecasting becomes something that organizations actively shape, not just observe. One important concept here is collaborative planning, forecasting, and replenishment, or CPFR. The main goal is to improve forecast accuracy through communication and coordination across the supply chain. By sharing information and discussing different scenarios, all parties can develop a clearer understanding and reach a common view of the future demand. CPFR is supported by information technology that allows data to be shared among partners, including downstream customers such as retailers and upstream suppliers. Well, it includes forecasts. The ultimate objective is planning. All right? Different parties share their forecast, revise them through discussions, and gradually move toward a consensus. Once that consensus is reached, each organization can align its own operations accordingly. This approach works especially well in business-to-business settings, where coordinating happens among relatively large organizations rather than many individual smaller consumers. For example, a retailer might first share a forecast based on a planned promotion in August. The manufacturer may respond that, their production capacity will be limited due to scheduled maintenance, making it difficult to support that plan. The retailer might then adjust the promotion timing or scale. Further upstream, a supplier may point out material constraints in certain months, leading to additional adjustments, right? Through this back and forth process, the supply chain eventually reaches a shared plan. Everyone understands the reasoning behind it, and all parties can coordinate their actions. This kind of collaboration can significantly improve overall planning and lead to better outcomes across the entire supply chain. So that's the end of this chapter. I do have a small, short demonstration using Excel spreadsheet.